Imagine you're standing in your kitchen. In front of you are two identical glasses of water. One is filled with hot water, almost steaming. The other is cold, straight from the tap. You place both glasses into the freezer. Same shelf, same position, same conditions. Now, a simple question. Which one freezes first? The cold one, right? Of course it is. That's the obvious answer. The cold water is already closer to freezing. It has less heat to lose, less distance to go. The hot water has to cool down first, catch up, and only then begin to freeze. So there's no competition. The cold water should win. Every time. Except it doesn't. Because sometimes, under real conditions, the hot water freezes faster than the cold. Let that sink in. Hot water, beating cold water in a race to freeze. It sounds wrong. It feels wrong. It shouldn't happen. And yet, it does. Now, here's the strange part. This isn't a new discovery. It's not something scientists just stumbled upon recently. People have been noticing this for thousands of years. As far back as ancient Greece, Aristotle wrote about it. He observed that water, which had been heated, sometimes cooled and even froze faster than water that hadn't. Think about that. One of the earliest thinkers in human history had already spotted something that still confuses us today. And it wasn't just philosophers. In cold regions, ancient fishermen were doing something unusual. Before freezing nights, they would warm their water first, then pour it around tools or supports to let it freeze. Why? Because in practice, the warm water froze faster. No equations, no thermodynamics, just observation. Real-world knowledge, built from experience. Centuries later, the idea resurfaced again. Francis Bacon mentioned it. René Descartes even tried to explain it. Descartes suggested that heating water removes certain particles, making it easier to freeze afterward. Not entirely correct, but surprisingly insightful for the time. And then, something strange happened. As science became more precise, as formulas improved, as laws of physics were written down, this idea slowly faded away. Not because it was disproven, but because it didn't fit the theory. So it was quietly ignored. Fast forward to the 1960s. Not in a high-tech laboratory, not in a famous university, but in a school kitchen in East Africa. There was a student named Erasto Mpemba. One day, his class was making ice cream. The process was simple. Heat the milk, mix it, let it cool, then place it in the freezer. But there was a problem. Too many students. Not enough freezer space. So Mpemba made a bold decision. He skipped the waiting. Instead of letting his mixture cool down, he placed it into the freezer while it was still hot. By every rule of physics, this should have been a mistake. But when he came back later, his ice cream was frozen solid. Others who had used cold mixtures were still liquid. Something didn't make sense. So he did what real scientists do. He didn't ignore it. He tried again. Same result. Again and again. The pattern held. But when he brought this to his teacher, the response wasn't curiosity. It was dismissal. This isn't real physics. His observation was brushed aside, even laughed at. But Mpemba didn't let it go. The question stayed with him. He kept experimenting, kept observing, kept asking, until one day an opportunity appeared. A visiting physicist named Dennis Osborne came to his school. After the lecture, Mpemba asked his question. This time, something different happened. Osborne didn't laugh. He didn't dismiss it. He said, "I don't know the answer, but I'll test it." And when he did, he found that Mpemba was right. In 1969, they published a scientific paper together, and for the first time this strange phenomenon had a name. The Mpemba Effect, a discovery that began not in a lab, but in a classroom, with a student who refused to ignore what he saw. Now let's step back and think like a physicist. Forget the story for a moment. Just use logic. You have two glasses of water. One is hot, one is cold. Which one should freeze first? The answer seems obvious. The cold water is already closer to freezing. It has less heat to lose, less energy to get rid of. The hot water, on the other hand, has a long journey ahead. It has to cool down, drop through every temperature, until it finally reaches the same point where the cold water started, and only then can it begin to freeze. So the cold water has a head start, and in a fair race, the one with the head start should win. Every time. This reasoning is backed by one of the most fundamental ideas in physics, Newton's law of cooling. It tells us that the rate at which something cools depends on the difference between its temperature and its surroundings. So yes, hot water cools faster at first, because the temperature difference is larger. But here's the catch. Even if it cools faster, it still has more heat to lose. And crucially, it must pass through every temperature that the cold water has already been at. So at some point, the hot water reaches the same temperature as the cold water had at the start, and from that moment on, they should behave exactly the same. Same temperature, same environment, same condition, which means the cold water should still win. The logic is clean, step by step, hard to argue with. But hidden inside that reasoning is an assumption so subtle, most people never notice it. We are assuming that if 2 glasses of water have the same temperature, then they are identical in every meaningful way. That temperature tells us the whole story. That a glass of water at 25 degrees Celsius is exactly the same, no matter how it got there. But what if that's not true? What if water that was once hot is fundamentally different from water that was always cold, even when they show the same temperature? What if the thermometer is hiding something? Because if that assumption breaks, then the entire argument breaks with it. And suddenly, the impossible starts to look possible. So now we investigate. If hot water really can freeze faster, something in our simple explanation must be missing. Let's treat this like a mystery. We have multiple suspects. Each one explains part of the story, but none of them has a perfect alibi. Suspect number 1, evaporation. Start with the most obvious. When water is hot, it evaporates. You can see its steam rising into the air. That means by the time the hot water cools down, there is less of it left. Less water means less mass, and less mass is easier to freeze. Simple, elegant, and definitely real. But here's the problem. Scientists have repeated this experiment in sealed containers where no water can escape, no evaporation at all, and yet the effect still appears. So evaporation helps, but it's not the whole story. Suspect number 2, dissolved gases. Water isn't just water. It contains tiny amounts of dissolved gases. Oxygen, carbon dioxide, nitrogen. When you heat water, those gases escape. That's why you see bubbles forming before boiling. So hot water becomes degassed, and that changes things. It can affect how water circulates, how ice begins to form, how easily crystals grow. Some scientists believe these tiny changes influence freezing behavior, and they're probably right. But again, even when researchers carefully control for gases, the effect doesn't completely disappear. Another partial answer, not the full one. Suspect number 3, convection currents. Now this one is powerful. When hot water cools, it doesn't sit still. It moves. Hot water rises. Cooler water sinks. This creates circulating currents, like invisible rivers inside the glass. These currents carry heat from the center to the surface, where it escapes faster. Cold water, by contrast, is much more still, less movement, slower heat transfer, and there's more. As water nears freezing, it forms an insulating layer of ice on top. That layer traps heat below it, slowing everything down. But hot water, with its strong internal motion, can delay that layer from forming, which means it keeps losing heat efficiently for longer. This is a major factor, but still, on its own, it doesn't fully explain everything we observe. Suspect number 4, environment effects. Now we look outside the water. At the freezer itself, imagine placing a cold glass on a frosty surface. The frost stays there, acting like insulation. But place a hot glass instead, and something changes. The heat melts the frost. Suddenly, the glass is in direct contact with the cold surface underneath. Better contact, faster heat loss. There's also another effect. A very hot object can raise the temperature inside the freezer slightly, triggering it to work harder. the cooling system kicks in more aggressively. So the hot water might not just be cooling itself, it might be forcing the freezer to cool it faster. But here's the limitation. These effects depend on the freezer type, the surface condition, the environment. Change those, and the effect can vanish. So again, real, but not universal. Suspect number 5, molecular structure, the deep one. Now we go deeper, much deeper, because water is not a normal liquid. It behaves in strange, almost unnatural ways. And the reason lies in something called hydrogen bonding. Water molecules stick to each other through these tiny electrical attractions. They form a constantly shifting network, breaking and reconnecting billions of times per second. Now here's the key idea. When you heat water, you don't just increase its temperature. You actually change its internal structure. Bonds stretch. Networks break apart. Energy gets stored inside molecular connections. And when the water cools, those structures don't instantly reset. They relax. They release energy. They behave differently. So, even if two glasses show the same temperature, their internal states can be completely different. One was never heated. The other carries a kind of hidden history, a memory, not in a mystical sense, but in a physical, measurable way. You could say, water remembers where it's been, and that memory can affect how it loses heat and how it freezes. Transition. Now here's what makes this problem so fascinating. Each suspect explains something. Each one is supported by real evidence, but none of them alone solves the mystery, which suggests something deeper. This isn't one cause. It's a combination, a conspiracy of physics, the hidden factor, supercooling. Now we come to one of the most surprising parts of this story. Water doesn't always freeze at 0 degrees Celsius. In fact, it can stay liquid well below freezing. This phenomenon is called supercooling under the right conditions. If the water is pure, if the container is smooth, if there are no disturbances, water can cool down to -5 degrees Celsius, muy gal, sometimes even lower, and still remain completely liquid. Think about that. Water, colder than ice, but not frozen. Why? Because freezing doesn't just depend on temperature. It depends on something else. Nucleation. That's the moment when the very first tiny ice crystal forms. It needs a trigger, a speck of dust, a tiny impurity, a scratch in the container, even a small vibration. Without that trigger, the water just waits. Balanced, unstable, ready but not frozen. Hot versus cold. What changes? Here's where things get interesting. Hot water tends to behave differently when it reaches this stage. Experiments have shown that water that starts hot often freezes at a higher temperature. In other words, it doesn't supercool as much. Instead of dropping to -10 degrees Celsius before freezing, it might begin freezing at -5 degrees Celsius. Why? Possibly because heating removes dissolved gases. It changes internal structure. It reduces barriers to crystal formation. The exact reason is still debated, but the effect is clear. The result: if hot water begins freezing at a higher temperature, then it starts the freezing process earlier. Even if the cold water reached lower temperatures first, it might still be stuck in that liquid, supercooled state, waiting, while the hot water has already begun turning into ice. And once freezing starts, it can spread rapidly through the entire container. Key insight. So the race isn't just about who gets colder first. It's about who starts freezing first. And because of supercooling, those two things are not the same. The big insight. So where does all of this leave us? We've looked at evaporation, convection, dissolved gases, molecular structure, supercooling. Each one explains something. Each one is real, measurable, tested. But here's the crucial point. None of them, on their own, fully explains the Mpemba effect. Not evaporation alone, not convection alone, not even the deep molecular changes inside the water. Individually, they're incomplete, but together, they start to tell a different story. Think of it like this. Imagine a race where one runner gets a slightly better start, another has better endurance, another takes a shorter path. Individually, None of those advantages guarantees a win. But combine them, and suddenly, the outcome changes. That's what's happening here. Evaporation reduces the amount of water. Convection speeds up heat transfer. Molecular changes store and release extra energy. Supercooling determines when freezing actually begins. Each effect is small, but they all push in the same direction, and when they act together, they can tip the balance. The deeper lesson. We often want simple answers. One cause, one effect, a clean equation that explains everything. But nature doesn't always work that way. Sometimes, an outcome isn't driven by a single reason, but by a combination of many small ones. A system of interacting effects, a kind of hidden collaboration, and that leads to a powerful idea. Nature isn't simple, and not every phenomenon has a single, elegant explanation. Sometimes the truth is messier, more complex, and far more interesting. Why it's still not fully solved. Even after all these explanations, one problem remains. The Mpemba effect is not consistent. It doesn't happen the same way every time. Sometimes hot water freezes first. Sometimes cold water wins. And sometimes there's no clear difference at all. This inconsistency is exactly why scientists still debate it, because the outcome depends heavily on small details like the shape of the container, the type of water used, tap, distilled, mineral, how clean or smooth the surface is, the exact starting temperatures, and even the specific freezer conditions. Change just one of these variables, and the result can completely shift. Conflicting scientific views. Because of this, researchers don't fully agree. Some scientists argue that, under tightly controlled laboratory conditions, the effect disappears entirely. In other words, they say it's not a real law of physics, just a combination of experimental side effects. But others disagree. They've designed experiments where the effect can be reproduced again and again under certain setups with specific conditions. Hot water really does freeze faster. The core problem. So the real challenge isn't just explaining the effect. It's this: defining when it happens and when it doesn't. Because the phenomenon sits in a strange space between reliable and unpredictable. It's real in some cases, absent in others, and sensitive to almost everything. The result, and that's why, even today, there is still no single, universally accepted explanation. Not because science has failed, but because the system itself is complex, fragile, and highly condition-dependent. The deeper lesson. At the heart of all this confusion is something surprisingly simple. Temperature is just a number. It's not a complete description of what's happening inside the water. It's only an average, a single value that represents the overall energy of billions of moving molecules. And averages can be misleading. Same temperature, different reality. 2 glasses of water can both read 25 degrees Celsius on a thermometer, and we tend to assume that means they are identical. But that assumption hides something important. Same temperature does not mean the same internal state. One glass may have been heated and cooled, different dissolved gases, altered molecular structures, different convection history. The other may have simply stayed at room temperature the whole time. To a thermometer, they look the same, but inside, they are not. A simple analogy. Think about 2 cities. Both have an average income of $50,000. On paper, they look identical, but in reality, in one city, almost everyone earns around $50,000. In the other, half the people are very rich and half are very poor. Same average, completely different society. Or think of sound. 2 pieces of music can have the same average volume, but one is smooth and steady, while the other is loud bursts followed by silence. The average hides the structure, the key insight. This is the real message behind the Mpemba effect. Measurements can simplify reality so much that they hide what actually matters. Temperature tells us how much energy is in a system on average, but it doesn't tell us how that energy is distributed, how the system got there, or how it will behave next. And sometimes those hidden details matter more than the number itself. Broader impact. The Mpemba effect isn't just about water in a freezer. Over time, researchers began noticing something even more surprising. Similar behavior appears in completely different systems, not just liquids, but also in other areas of physics. Beyond water, scientists have observed Mpemba-like effects in materials science, where certain systems relax faster when starting from a more excited or energetic state. Granular materials, like sand-like particles, cooling or settling in unusual ways, and even in quantum systems, where abstract particle models can reach equilibrium faster from higher energy starting conditions. This suggests something important. The Mpemba effect may not be a water problem at all. It might be a general feature of complex systems, the reverse Mpemba effect. Even more interesting, there's also a kind of mirror version of the phenomenon, the reverse Mpemba effect. In some cases, colder systems can heat up faster than warmer ones under the right conditions. So the asymmetry isn't just about cooling. It can work both ways, which hints at a deeper principle governing how systems move toward equilibrium, a bigger field of physics. All of this research connects to a growing area of physics called non-equilibrium thermodynamics. This field studies what happens when systems are changing, evolving, not yet settled into balance. And that's important because most real-world systems are never truly in equilibrium. They are always moving, cooling, heating, reacting, adjusting. The bigger picture. So the Mpemba effect may not be an isolated curiosity. It might be a clue, a hint that the path a system takes matters. History matters, and starting conditions can change how quickly equilibrium is reached. In other words, how something begins can shape how it ends. What physics students usually get wrong. Most people, even students who study physics, start with a very simple mental picture of cooling. They imagine it like this. A hot object is placed in a cold environment, and it just steadily loses heat in a straight, predictable line. Hot, then warmer, then cooler, and finally cold. Smooth, simple, linear. But that picture is wrong. The reality. Cooling is not a straight line. In real physics, cooling does not behave like a straight, clean graph. It behaves more like a curved, changing, and sometimes unpredictable process. At the beginning, heat loss is fast, because the temperature difference is large. But as the object cools down, that difference gets smaller, and the cooling rate slows down. So instead of a straight line, you get a curved cooling path that constantly changes slope. This is why real systems follow what we call nonlinear behavior. And in more complex conditions like water in a freezer, this behavior can become even more irregular and chaotic. The hidden mistake. Here's where most intuition breaks. People assume if something starts colder, it will always cool faster. But that's not how physics works. Cooling rate depends on many changing factors. Temperature difference, internal motion of the fluid, phase changes, like freezing, and even microscopic structure inside the liquid. So two samples of water can behave completely differently over time. Key insight. Just because one object is colder at the start does not mean it will always cool more efficiently later. And that simple misunderstanding is exactly where the Mpemba effect begins to feel so strange. Because once you realize cooling is not a straight line, the entire problem stops being obvious. The illusion of a simple experiment. At first glance, this looks like the simplest experiment in the world. You take 2 cups. You fill one with hot water, one with cold water. You put them in a freezer. That's it. No complex setup. No expensive equipment. Just 2 containers and time. So naturally, people assume the result should be straightforward. But reality is far more sensitive. In physics, the moment you actually try this experiment carefully, something surprising happens. Tiny changes completely change the outcome. What seems like a simple test turns into a highly sensitive system where small details matter a lot more than expected. For example, the shape of the container can change how fast heat escapes. The material of the surface affects thermal contact and conduction. Even the air movement inside the freezer can shift cooling rates. And that's just the beginning. Everything becomes a variable. Once you look closely, nothing is truly simple anymore. A slightly different glass shape can change convection patterns inside the water. A different plastic or metal surface can speed up or slow down heat transfer. Even opening the freezer door at the wrong time can disturb airflow and temperature stability. Each factor on its own may seem small, but together they completely reshape the experiment. Key message: what looks like a simple kitchen test is actually an extremely sensitive physical system, and that's the real reason the Mpemba effect is so difficult to pin down. Because when the system is this sensitive, small, hidden differences can decide the outcome. Why freezers are not perfect science tools. It's easy to imagine a freezer as a perfectly controlled environment. You set the temperature, close the door, and assume everything inside stays uniform and stable. But in reality, that picture is far from true. A household freezer is not a laboratory instrument. It's a complex, messy, dynamic system. Uneven temperature inside. Inside a freezer, the temperature is not the same everywhere. Some areas are colder. Some are slightly warmer. Some spots cool faster depending on their position near the cooling coils. So two identical cups placed just a few centimeters apart may actually experience different thermal conditions. Constantly changing airflow. Then there's air movement. Cold air is constantly circulating inside the freezer, but not in a perfectly stable way. Every time the compressor turns on or off, every time the door opens, even every slight disturbance changes airflow patterns. This means heat is not removed evenly or predictably. Frost and ice build up. Over time, frost begins to form on surfaces, and that frost matters more than most people realize. It acts like an insulating layer, changing how efficiently heat can flow from the container to the freezer walls. But here's the key point. Frost does not form uniformly. It builds in patches, grows unevenly, and constantly changes the thermal landscape inside the freezer. Final insight. So when you place 2 cups of water inside a freezer, you are not placing them into a perfectly controlled experiment. You are placing them into a system that is already uneven in temperature, unstable in airflow, and constantly changing due to frost and ice. Which leads to one important conclusion. Even your freezer becomes part of the experiment itself. So where does that leave us? Even after centuries of observation, after countless experiments, and after all the proposed explanations, we still don't fully understand why hot water sometimes freezes faster than cold water, and that might feel disappointing at first. But in science, uncertainty is not a failure. It's an opportunity, because it means there is still something left to discover. The real lesson of science. The Mpemba effect teaches us something deeper than physics. It reminds us how science actually works. Observation comes before authority, not the other way around. It doesn't matter how clean a theory looks on paper. It doesn't matter how confident the equations feel. If reality shows something different, then reality wins. Every time. The Mpemba reminder. That's exactly what happened with Aristotle Mpemba. He didn't start with a theory. He didn't have advanced tools or formal training. He simply noticed something unusual and refused to ignore it. Even when he was told it couldn't be true. Even when he was laughed at. He trusted what he observed over what he was told. And that curiosity, more than anything else, is what brought this question into science. Final thought. In the end, the lesson isn't just about water. It's about mindset. Because real discovery doesn't always come from credentials, or authority, or perfect knowledge. It often comes from someone asking a simple question. Wait, why is this happening? And sometimes, that question changes science forever. Call to action. Now here's something you can try yourself. Go to your kitchen. Take 2 identical containers, 2 cups or glasses. Fill one with hot water from the tap. Fill the other with cold water. Place them side by side in your freezer. Same shelf, same position, same conditions. And then, wait. Check on them periodically and observe what happens. Does the cold water freeze first, as expected? Or does the hot water surprise you? Now ask yourself, which one froze first in your case? And more importantly, why do you think it happened? Was it evaporation? Convection? Supercooling? Or something deeper you can't immediately see? Because the real science doesn't end with the experiment. It starts with your curiosity.